Hi, my name is Aaron Chan, and I'm a PhD candidate at USC. In this talk, I'll be presenting our work on learning from knowledge graph explanations for common sense reasoning. So, what are knowledge graphs? Well, a knowledge graph, or KG for short, is a type of knowledge base that represents knowledge as a directed graph of entities and their relations. In a KG, nodes are entities while edges assert the relations between entities. In this example, we show a KG subgraph extracted from ConceptNet, which is a commonly used KG. KGs contain facts, which are triples of the form entity1 relation entity2. Note that edges are the same as facts. Also, a path is a connected sequence of facts in the KG. For instance, child capable of sit and classroom synonym schoolroom are facts, while child capable of sit used for desk is a two-hop path. KGs can contain an enormous number of facts. In particular, ConceptNet contains about 21 million common sense related facts. Thus, KGs can serve as rich information resources for solving knowledge-intensive common sense reasoning tasks. In this work, we focus on the Commonsense QA task, a standard task in common sense reasoning. In Commonsense QA, the goal is to predict the answer to a multiple choice question, which requires common sense to solve. Here, the question is, where does a child likely sit at a desk? However, since, by definition, common sense is self-evident to humans, common sense knowledge is rarely stated explicitly in natural language. This makes it difficult for models to learn common sense knowledge from text corpora alone. To address this limitation, many works have proposed augmenting common sense QA models with common sense KGs, such as ConceptNet, which store abundant information about common concepts and the relations between them. By reasoning over facts in the common sense KG, the model leverages valuable background information that help predict the correct answer schoolroom. Now let's talk more about the structure of KG augmented models. Generally, KG augmented models consist of a text encoder, graph encoder, and task predictor. The model's workflow is as follows. First, the task input is fed into the text encoder in order to obtain the text embedding. For Common Sense QA, the task input would be the question and one of the answer choices. Typically, the text encoder is a transformer-based language model, such as BERT. Second, the KG and text embedding are fed into the graph encoder, which updates node or path embeddings, then outputs the graph embedding by intentional pooling of node or path embeddings. To solve a given task instance, the full KG generally contains too much irrelevant information. So in practice, the KG we feed into the graph encoder is a smaller contextualized KG, which is constructed from the full KG with respect to the task instance. Usually, the graph encoder is a GNN or path aggregation model. Finally, the text and graph embeddings are fused and fed into the task predictor, which gives us the task output. For Common Sense QA, the task output would be a plausibility score for the question and given answer choice. Also, the task predictor is usually an MLP. There are several advantages of using KG augmented models. First, the KG can provide abundant common sense knowledge beyond just information from the task input and text corpora. Second, reasoning over the KG's symbolic structure serves as a strong inductive bias, which can improve generalization to unseen data. Third, KG augmented models can explain their predictions through attention over the KG nodes or paths. However, KG augmented models also have some key limitations. First, for a given task instance, the KG may not be useful, and not all parts of the KG may be useful. Second, existing KG augmented models are only trained with the task labels and are not explicitly taught when the KG or specific parts of the KG should be used. Meanwhile, KG saliency explanations can indicate which KG inputs most influence the model to make the correct prediction. KG saliency explanations are created from the model and task labels by using saliency methods, which can be gradient-based, occlusion-based, etc. Now we introduce SalKG, the proposed framework for training KG augmented models with saliency explanations. The key idea is to use KG saliency explanations to regularize the KG augmented model's attention mechanism. First, we train the teacher KG augmented model on the given task. Second, we use the teacher model to create coarse and fine KG saliency explanations. Coarse explanations are graph level and tell us if the KG is useful for solving the given instance. Fine explanations are node or path level and tell us which nodes or paths in the KG are useful for solving the given instance. And third, we train a student KG augmented model to predict the saliency explanations, then solve the task by attending to KG features highlighted by the predicted explanations. Here, we see that the student model is trained by jointly optimizing the task loss L task and the explanation prediction loss L sal. Now let's take a look at some results on the Commonsense QA dataset. We consider several vanilla baselines shown in yellow. NoKG is a language model that doesn't use a KG. KG denotes the original teacher KG augmented model, and NoKG plus KG is a simple mean ensemble of NoKG and KG. Furthermore, hybrid is a variant of SalKG that uses both coarse and fine explanations. And finally, RAND is a baseline variant of SalKG that uses random explanations. Here we see that SalKG outperforms NoKG, KG, NoKG plus KG, and RAND. This shows that saliency explanations can provide strong signal for teaching KG augmented models to focus on useful KG features. We also find that SalKG hybrid performs the best overall, beating both SalKG coarse and SalKG fine. This suggests that coarse and fine explanations are complementary. For results on other models and datasets, plus more details about experiments, please refer to our paper. In the future, we plan to explore several interesting directions for building upon SalKG. First, we aim to incorporate active learning into SalKG in order to provide KG augmented models with targeted human feedback about KG saliency. And second, we would like to design new ways to train the model using KG explanations, beyond just attention regularization. If you'd like to learn more about our work, please check out our paper and come visit us at the XAI workshop at ICML 2021. Thank you.